मॉर्निंग क्लास। आज हम लोग एक एक्सपेरिमेंट परफॉर्म करने वाले हैं एक साथ। हम लोग स्प्रिंग के स्प्रिंग कांस्टेंट को कैलकुलेट करेंगे। तो आप सब लोग अपनी कॉपीज़ के साथ रेडी हो जाइए। ये आपको अपनी प्रैक्टिकल कॉपी में नोट करना है। आपको ऑब्जेक्ट टू फाइंड फोर्स कांस्टेंट ऑफ अ गिवन स्प्रिंग. Then you have to write apparatus, which is a vertical stand, a different set of masses, scale and spring. And here is the apparatus which we are going to use. You observe this apparatus. Since I have to manage the camera and the apparatus by myself, so there will be little disturbance. I hope you can bear it with me. So you observe the apparatus shown to you. Here we have this scale which will help us to take the readings. There is a pointer. Can you see the pointer? And the spring. I don't know whether in the dark background you can see the spring. So let me use a bright background so that you can observe the spring we are using. Yes, now can you see the spring better? And here is this one, a hanger. Right, in which we will suspend different masses. These are the masses which we are going to use. This is 50 gram mass, 20 gram. If you can see, I want you to have a first hand experience as we used to have in the lab. If you can see the 20 gram, let me manage this is 20 gram, I think now it's visible. This is 50 gram, right bacha? Then we have 20 gram, one more, and then we have this 10 gram. Now what is the use of these weights? That we will use these weights, we'll suspend these weights in combination, and we'll check what is the extension in the spring with help of this pointer. Right? First we will take the original length of this spring without suspending even a single weight here. This pointer's position will give us the measurement of original length of this spring. After that we will suspend the shown weights one by one here, and you can easily guess that when we will suspend a weight here, due to force exerted by that weight, the spring will be pulled down. So this pointer will move down. The new position of pointer will be recorded by us, and the new position of pointer, that reading minus the original position of pointer, that reading will give us extension of the spring for that particular weight. We have to draw observation table, and in one column we will write the mass suspended. In the other column we will write the position of the pointer for that mass. In the third column we will subtract the position of the pointer for the mass minus the original position of the pointer when no mass was suspended, and then this subtraction will give us the extension of the spring. After getting 5 extension readings for 5 different masses, we will draw a graph, mass on y-axis and extension, mass on x-axis, and extension on y-axis. So that part is the second half of the experiment. After writing this object and apparatus, let us understand first the principle behind this experiment. So, let me keep this apparatus aside so that I can show you the board. Children, this is the original length of the spring, which is represented with alphabet L naught. When you suspend the mass, due to gravity, mass will be pulled down. As a result, the spring will be elongated. The force exerted by the weight is called deforming force. I hope you are noting it down. The force exerted by the weight is called, yes, it is called deforming force. Just actively participate with me in the class and keep on answering me even if you are at home. If this spring is stretched, if you hold a spring and stretch it, you will experience a force inward on your hands. Why? Because when you change the length of the spring, more general term is deformation. When you deform the spring, there is a strange kind of force appearing in the spring. That is called restoring force. Why restoring force? Because when you pull the spring, this force is appearing just opposite to the force exerted by you, and its tendency is that a spring should restore its original length. That is why it is called restoring force. As class 10th is also having a spring force in their syllabus as a contact force, so this whole experiment and the explanation is very useful for class 10th also. So you can share to your class 10th friends that they can go through this topic here. So restoring force is actually Hooke's law gives us a very specific characteristic of this force called restoring force. Hooke's law says that this is not a constant force like the force of gravity. It's a variable force. This restoring force is directly proportional to the extension, elongation of the spring. And more is the elongation, more will be the restoring force. So you can easily understand that when you replace this proportionality sign, you have to put a constant here. So restoring force will become a constant times elongation. This constant is known as force constant. This constant is known as force constant or spring constant. Force constant or spring constant. And we have to find this spring constant through our experiment. Right? Now this force constant or this restoring force since it depends not this force constant is a constant for a given spring. This restoring force, since it is a variable force, so when you increase, when the length of the spring is increasing because of the gravity, as soon as the gravity starts pulling the mass down, the spring starts getting elongated. If I hold the spring here and we take it as the point of suspension and I start pulling the spring, as soon as the spring starts elongating, and especially if I put a constant force of this weight, constant force, this is 10 grams weight, so 10 into 1000 centimeter per second square, that is the G, or 980 centimeter per second square. So when there is no mass, the spring is in its original length, but as soon as we suspend the mass, spring, since this mass is light enough, so spring is elongated a little. And as soon as the spring elongates, initially actually spring starts elongating, if we can see it in slow motion. This constant force pulls the spring down, and as soon as the spring starts stretching, this force, restoring force, develops in the spring. But this restoring force is a variable force which depends upon the stretching or the elongation. So as soon as this mass is pulling the spring down, this restoring force keeps on increasing. This restoring force is increasing. Understand this point. This restoring force is increasing, but the force, that is mg, is a constant. So of course, as the spring gets elongated more and more, this x is increasing, so the restoring force is also increasing. And there will be a situation when this restoring force will become equal to mg. When this restoring force will become equal to mg, then this mass will come in equilibrium position, that is at rest. And that is the point when we have to take the observation. And as I said, if we are able to arrange some high definition camera, and if I can show you that what happens when we suspend this mass here, let me take the heavy mass. And if we take the heavy mass, you can easily understand that the duration which we are not able to observe here, that duration during which this spring is elongated. See, during which this spring is elongated. Can you see this? That if I suspend it and this spring is elongated, so actually it takes few seconds, and those are the seconds during which, see, those are the seconds during which this is normal position, and this is the time when a spring, few seconds, fraction of second, during which this spring gets elongated, and that is the time during which the restoring force increases. And finally it attains the force, that is 20 gram into gravitational acceleration. And when the restoring force is equal to 20 g, then this mass comes into the rest position. But that happens in fraction of seconds. So you are not able to see the whole process. But yes, if I will be able to find any such video performed by any prestigious university that is available on YouTube, I'll certainly give you link of that video. So let me start our experiment. you copy all this principle, object and apparatus. So class, can you see we have a principle written on the left side of the board and an observation table on the right side of the board. This principle says that we are going to note down the readings when restoring force is equal to the force, the deforming force. Restoring force Kx is equal to gravitational force mg. So K can be written as mg upon x. Then take the m upon x separately and g here. We have to draw mass versus x graph. Slope of mass versus x graph is this m upon x. From the graph, we will take this m upon x value by calculating the slope of the graph, and then we will substitute it here. We will write the value of g here. All the units we will place in SI unit, and then the product will give us force constant. Observe the way I have written the observation table. This is very important for boards. This year also, since all of the students followed the instruction, so I am so glad to announce that most of the children got full marks in practical, because in their copy they have not done any mistake so that examiner can deduct the marks there. So you also have to aim that full marks in practical. So the first point, before we write the observation table, position of pointer when no mass is suspended with the spring, we will represent it with L0 and write here the value with centimeter unit. Don't forget writing unit, your mark will be deducted. Then make 4 columns. One is for serial number, the second, just observe it, mass in grams. This is compulsory. Then position of the pointer when that mass is suspended in centimeters. Here you write in centimeters. Then we have to calculate L minus L0 each time when we will suspend a new mass, and that will be the extension x of the spring, and L minus L0 will also be in centimeter. So first you note down this observation table, be ready with a pencil to note down the readings along with me, and then I start experiment. So are we ready for the experiment, children? I have the vertical stand, this scale and the spring system arranged in front of you. I arranged this scale in such a way that I can clearly note the pointer's position through the scale. And now I'll start my experiment with 10 gram force. I'll suspend, but before we start it, let me note down the reading of the pointer when no mass is suspended. And I want you to note, let me focus the camera so that you note the value by yourself. It will take a little time to arrange the reading, and now I think you are able to note the position of pointer. So tell me, beta, what is position of pointer? Is it visible to you? Yes, now it's quite visible to you. Note down the position of pointer, and this is one thing you have to understand, that the 0 of the scale is at the top. So we have to find the reading coming down. So this is, see, this is 16, then this is 15, 16, and then this is 17. So the reading is 17.5. Check it out, beta. Reading is 17.5. So before the mass is suspended, let me cross check it. Yes, reading is 17.5. All of you can see it? Very well. So note it down in your observation table. So first reading is 17.5 centimeter. Very important thing. Whatever reading we are taking from the meter scale, least count of meter scale is 0.1 centimeter. 0.1. That means the first decimal place is 0.1, means first decimal place is in the least count. So children, it is very necessary that whenever you write any reading from this meter scale, you have to write it up to first decimal place. If nothing is there at the first decimal place, then write 0.0. But never write reading from the scale as 17. If it is 17, then also you have to write 17.0. So now, after noting down the position of pointer when nothing is suspended with the spring, let me suspend a 10 gram mass. Can you see? I am suspending a 10 gram mass. I have suspended 10 gram mass, and now again we have to find the reading, right? So let me focus on the scale. So now it's focused, and I think you can see when we suspended the mass of 10 gram, then what is the reading of the pointer? It is beta 17.6, and you can take 5, 6, 7. It's 17.7. See? 6 is visible to us. The pointer is in front of 7. So the reading is 17.7. For what mass? Mass is 10 grams. So let me write this 10 grams mass and 17.7 reading. So right here mass is 10 grams and the reading is 17.7 centimeter. Let me focus again on the observation table. Can you see it now? So note down the reading 10 grams and 17.7 centimeter. And now we are going to suspend 20 gram mass. Now let me suspend a 20 gram mass with the spring. We have to remove this 10 gram mass and we have to suspend a 20 gram mass. And you can see that now the position of pointer has changed. So again we have to focus on the scale so that you can yourself at your study table get the original readings. Now children, try to get the reading now, the new position of the reading. And if this pointer we take it horizontal, then can you see it is 17.5, 6, 7, 8 and 9, because it is in front of 9. 8 is visible to us, right? So it is 17.8, 17.9. All of you can see it. Once the orientation of pointer is set, we don't have to change it in every reading, otherwise the error will be there. So it is 17.9 centimeter. So now let me focus again on the observation table and write the readings. All of you write here, it's 20 gram and reading is 17.9 centimeter. We will perform the calculation part at the last. First we will note down all the readings. Now we are going to suspend 10 gram weight more. So 20 is already there and this 10 gram weight will make the total mass suspended 30 grams. So let me suspend the 30 gram mass here. Right? All of you can observe it. And now again I have to focus on the scale so that you can take your readings in your copy. Now see children, what is the new position of the pointer? Take the reading by yourself. It is 18.1. Getting it? 18.1 centimeter and the mass suspended is 30 gram. So let me focus on the observation table again and I should keep this aside, and now you note down the new readings, that is 30 grams and 18.1 centimeters. Now I'll keep 30 gram is there. I'll place one more 20 gram here so that the next mass is 40 grams. So now children, I am suspending this 20 gram mass by removing 10 gram mass so that the total mass suspended is 40 grams. Can see it? And now we have to again focus on the scale so that we can take the reading. Now children, just observe the reading with the 40 gram mass. This pointer is little tilted, so we have to take care that it should remain in all the set of observations so that we don't have the error because of the change of the orientation of the pointer. So now here it is 18.5, 1, 2, 3, 4. It's 18.4. Can you see it? 1, 2, 3 and 4. So now for 40 gram, the reading is 18.4. Don't see the pattern in the reading. Don't take pain of this thing that pattern is not coming, like 0.2 difference is not coming in the readings. That we have to sort it out in the graph actually. So now let me focus the camera on the observation table, and I should shift it here, and I am going to write the reading for 40 grams. So her reading is 40 grams and this is 18.4 centimeter. Clear? Now the last reading of this experiment, that is 50 gram, and we already have 50 gram weight with us. So I'll remove these 20 gram weights and I'll suspend this 40 gram weight with the hanger. Right? And now I am going to focus the camera on the scale. All of you keep on writing all the readings because you have to write it in your practical copy class. Now check out by yourself the reading for the 50 gram class. This is 18.6. See, 18.5. The fifth line we can see. So the pointer is actually, this is the problem of the camera, that we have to adjust our observations according to the situation given, and you can see it's 18.6. 5 is visible to us, so the pointer is in front of 6. 18.6. So let me note down the reading by focusing our camera on the observation table, and I remove this apparatus in front of you so that now we can calculate the third column of also. So let me write, it's 50 gram and the reading is 18.6 centimeter. And now we are going to write the next column, that is L minus L naught. You observe the way technically the numbers have to be written. 17.7 minus 17 every time you have to subtract from L naught. 17.7 minus 17.5, so it will be 0. Let me use the yellow color only. 0.2 centimeters. Then 17.9 minus 17.5. You don't have to subtract 17.9 minus 17.7. Every time you have to subtract the new pointer reading and the original length of the spring. Then only you will get extension for that particular mass. So 17.9 minus 17.5 is 0.4. 18.1 minus 17.5. Write it here. It will be 6. 0.6. Keep on calculating along with me and check if I am not doing any wrong calculation. 18.4 minus 17.5. So this will be 0.14 minus 5, that will be 9. Right? And then 18.6 minus 17.5. So this will be 1.1. So now the whole experiment is done. We are having our observation table with us, and now it's time to draw the graph. The very important fine points for your board exam, I have explained it in the previous experiment, that was the resonance length versus frequency of the tuning fork experiment. In that experiment, during the graph formation, I have shown you what points you have to take care, how to take scales, and how to take scale, then how to plot the points with a very fine pencil, then how to calculate slope, what things you have to mention in the graph. This experiment, again I'll explain you those things, and you are lucky enough that you are having all these experiments. You, class 10th, class 12th, all students are having these experiments forever in the YouTube, and even before the exam you can go through these classes and can revise. So utilize every opportunity given to you. So children, now we are shifting to our table and we are focusing our graph. You note down all the readings I am giving you time so that you can copy all the important things written on the board.